I welcome you to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Psychophysical Systems, IISc. Today's talk is by Dr. K.P. Naveen, and he would be giving a talk on Bayesian Game-Theoretic approach to mobile data offloading. Dr. K.P. Naveen received his BE degree from VTU in 2005 and the Ph.D. degree from Department of Electrical Communication Engineering, IISc Bangalore in 2013. His work experience includes Scientist C at ISRO Satellite Center, Bangalore, postdoctoral fellow at INRIA Saclay, France, and Inspire faculty at the Department of Electrical Engineering, IIT Madras. Since July 2017, he is with the Department of Electrical Engineering, IIT Tirupati. His research interests include performance analysis of wireless networks, network economics, game theory, and optimal control. Over to you, Dr. Naveen.
Thank you for the introduction. So let me go into the details of my talk. So the presentation is going to be about Bayesian game-theoretic approach to mobile data offloading. So I have dual objective here. So one is to introduce this proposal of mobile data offloading, and also talk about about Bayesian game, and to show how to apply technique from Bayesian game to solve some interesting pricing problems that arise in the context of data offloading. So I'll start with a brief introduction to motivate the particular setting that we are interested in. So over a few years, everyone would agree that we have been witnessing an ever-increasing demand for mobile data. And it's primarily due to several data-intensive applications, right? Live TV. And so these days, majority of the calls is always over video. And also online gaming is becoming very popular, right? And now, so in addition to this, the ongoing pandemic crisis has also given rise to a scenario where several activities which otherwise used to happen physically, right, are going online, right? For instance, online classes, meetings, and even big conferences are happening, are going virtual these days, right? So all these are going to add up to the demand for mobile data. And also, so it's not just these human-centric applications, right? So even in future, there are a lot of machine-centric applications that are planned to be deployed. Right? So particularly home automation, some of which we are already seeing now. So some auto lights, auto fans, and so on, and some delay sensitive applications like self-driving cars. We are talking about Industry 4.0 and smart healthcare and so on. Right? So both these human-centric as well as machine-centric applications is definitely going to add up enormously to the existing demand for mobile data. So here, I would like to mention that so the blame is not just on the new applications. Okay, so there's some kind of a cycle going on where one is feeding into the other, right? So the newer applications is adding to the demand for mobile data, but also as and when the operators are start providing more and more data, so that is acting as a catalyst for the developers to come up with newer applications which are much more data intensive, right? So we are talking about virtual reality, augmented reality, and so on, right? So again, that will add up to the demand for mobile data and so on. Okay, and so this process, this trend is going to continue into the future, and the demand in a couple of years, few years down the line, is going to be very extensive. Okay, so now how are we going to meet this demand? So definitely, so 5G and even the next generation cellular networks are definitely attempting to solve this problem of demand for mobile data. So some of the novel features that 5G tries to bring in, so I'm just highlighting few of them. So one is to get more capacity. The obvious approach is to pump in more spectrum, right? So that's what the 5G attempts to do. So they propose the new radio frequencies. So we are planning for sub-gigahertz, right? So for the cellular operator, sub-gigahertz band has been opened up. and even millimeter wave more than 24 gigahertz is also available, will be made available for the operator. Okay. Now, so these are licensed bands. So in addition to this, so there is also opportunity for the operators to use the unlicensed band, right? So just like LTE unlicensed, we can also talk about 5G unlicensed. Okay, so here in an opportunistic fashion, the cellular operators can start transmission in particularly the Wi-Fi band. Okay. So now the other approach which 5G employs is to exploit the spatial dimension. So already the time and frequency dimensions have been extensively exploited. So now with massive MIMO, there is a scope to increase the capacity by few fold, right? So we are talking about something like 64 cross 64 antenna system, where easily up to 5-fold increase in capacity is possible. Okay. So this is another novel feature through which 5G attempts to meet this growing demand. Then the other approach is by spatial reuse. So the idea is to deploy large number of femto and pico-cells. And this is in addition to the existing large cell base stations, which are already operated by mobile operators, right? And now, so these small cells could be owned by private operators. So for instance, you can think of an installation in a campus setup, right? So set up by the institute, or even some private companies owning such small cell base station for service to their employees. Okay. So when we have a setting like this, right, it gives the possibility of offloading some of the users of the mobile network operators onto these small cell base stations, right? So of course, there are a lot of engineering challenges involved in enabling this technology, right? So you have to smoothly hand over an user who is already subscribed to a mobile network operator to one of the small cells, right? So a lot of engineering challenges are involved. But even when those engineering challenges are enabled, so eventually, so there are a lot of economics at play here, right? So since data offloading is not for free, right? So some incentivization is necessary. And once revenue is involved, so a lot of economics will come into play for the both MNOs, mobile network operators, as well as the small cell providers to take advantage of this process of data offloading. Okay. So this the focus of this talk will be on the economics of this mobile data offloading. Let me take you through what is involved here. So the key stakeholders are these mobile network operators and the small cell service providers. So all are privately owned operators. And now the MNO so once we have a setup like this, so MNO has the option of offloading some of its users onto SSP, right? So this way the MNO can increase its capacity, or it can offer subscription to more number of users, right? And that way the user experience throughput is going to increase. Okay, so this is essentially the offloading problem. But what we are primarily going to be interested in this talk is the SSP's problem of setting competitive prices, right? So as I mentioned earlier, so these SSPs could be owned by different operators, different private parties, right? And now, since several such parties are available for the mobile network operator, SSPs better have to set competitive prices, right? So to make revenue out of this process of offloading. Okay, so that is going to remain the focus of the presentation. So essentially, what we will do is we'll formulate a pricing problem and capture it using the framework of Bayesian games. Right, so that is the primary focus. And also, so this is joint work with my PhD student Sushma, and so this is an ongoing work. So currently, we are also focusing on solving the offloading problem, right? So at a higher layer, the MNO also can choose to decide how much of traffic it can offload onto the SSP. So in the context of offloading problem, I'll very briefly, depending on the availability of time, mention about this ongoing work as well, right? So here we formulate using Stackelberg game. Okay, right. Okay, so with this introduction and motivation in place, I'll proceed now. So this is going to be the outline. Yeah, yes.
Yeah, may I ask you a question?
Yeah, sure.
Yeah, Shamar is here. So basically, for this offloading part, in terms of offloading, we have two things. One is computational data offloading. Other one is the handover type of thing. Like suppose MNOs instructs the mobile user equipment to connect with SSP, right?
Yes.
So are you considering both aspects or the handover type of thing you are considering?
I am considering the handover type, actually, the traffic essentially.
Okay.
Yeah,
not the computational.
Not the cloud computation type, just the handover of the traffic data. So the mobile users, I expect to be completely handed over to the SSP.
Okay, thank you.
Yeah. Right. Yeah. Thanks. And so this is going to be the outline. So I'll explain the model in greater detail here. I'll talk about the pricing problem. So we'll formulate using Bayesian games. And then we'll characterize the solution using Bayesian Nash Equilibrium. So I'll talk about both the Nash Equilibrium in pure strategies as well as in mixed strategies. So then we'll do a comparison with a non-Bayesian scheme. And so the comparison will be in terms of price of anarchy. So we'll do that comparison here. And then, so depending on the availability of time, I'll briefly mention about this ongoing work on the MNOs offloading problem, and then I'll draw my conclusion. Okay. Right. So I'll set up the model here. So feel free to interrupt me and ask any queries related to the model. So objective is to get through the model as clearly as possible. Right. So So I have just for simplicity, I've just reduced the illustration. So whatever I'll discuss is applicable to a network with more MNOs and SSPs also. Okay, so I'll mention about that in a while. So here is the model. So I'll assume that there is one mobile network operator, and let's say there are two competing SSPs. So they are owned by competing operators. Say. So I'll call it as SSP1 and SSP2. And now we'll talk about two types of flows. So one is the monopoly flow. I've been talking about the mobile unit, right? So the user, right? So let's say the user in this particular region. Okay, so this is the overlap region. But leaving the overlap region, so all users in this region were subscribed to the mobile network operator, right? So the traffic generated by them, I refer to it as the monopoly flow. So why monopoly? Because if at all MNO decides to offload, it has to only offload to SSP1, right? So SSP1 has monopoly over the traffic generated by those users, right? So I'll call it as a monopoly flow. So there's Fi for SSPI, right? So F1 and F2 are the monopoly flow. And users in this overlap region, I'll call it as the overlap flow. You can call it as the duopoly also, because the users in this region can be offloaded to any of the SSP, right? So Fi and F0, right? So this is the aggregate request for traffic generated by all users in the respective region. Okay, so I'll use this notation Fi and F0. So what is the particular flow model that we will consider? Now, the users in this region, the request for traffic generated by them is actually private information of individual SSPs, right? So SSP1 may have some information about F1, but not about the traffic generated by users in this region, right? So this is the users in the coverage region of SSP2. Okay. These are private information. So we'll start with a very simple model. So I'm going to model them as IID random variables. And further to simplify, so let's say that there are only two flow levels. Okay, the flow is either low or flow is either high. Okay, so low with probability theta and high with probability 1 minus theta. Okay. So we'll start with it's a very simple binary model. So later we'll generalize it to a setting comprising multiple flows of several different flow levels, right? Okay, and then yeah. So when I say private information, SSP1, okay, SSP1 knows the information about F1, but not about F2, and vice versa at SSP2. Okay, so that's what I mean when I say that F1 and F2 are private information. So what is F0? So F0 is the aggregate traffic generated by users in the overlap region. And I'll assume that it's common information, so commonly known to both the SSPs. And we'll simply, it can be arbitrary, but it's a constant, and let's say it's commonly known to both the SSPs. Okay. So this is the flow model. And now, yeah. So this illustration, so this simplified illustration was, so it can be extended to a much bigger setting also. But only constraint is that, so I'm assuming that these MNOs belong to the same operator. Okay, so these base stations, and their SSPs owned by two competing operators. Okay, so SSP1, so maybe they have some set of base stations deployed. So similarly, SSP2 may have some set of base stations, right? So now F1 will constitute the traffic generated by users in all these regions, okay? So owned by SSP1. And F0, the overlap flow, is the flow in the overlap region, or the traffic generated by users in the overlap region. Okay? Here I've shown just two overlaps here. So there's one overlap here and one here. So in general, there can be a good amount of overlap in metropolitan cities particularly. Okay, fine. Right, so let me stick to this illustration for simplicity.
Hello, Naveen, one quick question.
Yeah, sure.
In the picture, in this picture, does it matter there are more than one MNOs?
It can be actually. So only thing is that I'm assuming that all these MNOs are owned by a single operator.
So I mean, the way you explained, having multiple SSPs will not change, will not alter the problem.
Yes, yes.
But having more than one MNO, will that change the problem?
Yeah, I see actually, because the offloading, there is constraints on offloading, additional constraints on offloading. Yeah, I see that. Yeah. So it may require a slightly more detailed model. So more constraints will come in. Right. True. Yeah, I agree. Yeah. Yeah. Okay. Yeah. So that will bring in more constraints. So maybe perhaps in future scope we can address those. Okay. So let's yeah. So from this simple model, so we'll try to draw some insights. So first is let's talk about the pricing strategy of the SSP. Okay. So we'll assume, or we'll enable the SSPs to set prices in dynamic fashion. Okay. Or we'll call it as the flexible pricing scheme. So here, so I've introduced this random variable Pi, P1 or P2. Okay. So depending on the SSP. Now, when the flow is low, so this is the price announced by the SSP, right? So, and then when the flow is high, so this is the price announced by the SSP. Okay, so what are these prices? So these are the prices charged to the MNO for serving per unit flow, or for offloading per unit flow of traffic. Okay, so these are per unit flow prices. So it will become clear when I talk about the utility functions shortly. And I'll call this as the price vector of SSPI. Essentially, this is going to be the action of each of the SSP. Okay, so P1 and P2. So we have this price vector. Okay. Now, so before I complete the model, so let me introduce some more notation. So CS, I'll denote CS as to be the cost incurred by the SSP to serve 1 unit flow of traffic. Okay, so so this is the cost model at the SSP, and the MNO has to charge something to its subscriber. So we are assuming that it is going to charge a flat price of PM. or per unit flow of traffic. Okay, so PM is the price charged by the MNO to its subscriber, and this PI is the price charged by SSPs, each of the SSP to the MNO. Okay, so this is a random quantity. Depending on the flow level, a price will be fixed. But once a price vector has been announced by SSP, so we have a distribution on PI as well. Okay, fine. So so let's just take a note of one point here. So this price strategy should fall in this interval between CS and PM. So why is that? So if PI is more than the price charged by the MNO to its subscriber, the MNO has no incentive to offload. Okay, so price better be less than equal to PM. And also if SSP chooses a price less than CS, so then there is no incentive to serve actually. So it cannot make any profit serving the flow, right? Offloaded flow. So that way, so this actually serves as this interval serves as the action space for setting prices for the SSP. Okay. Right. So now, so let me proceed to the revenue model. Okay. So once the price vectors are announced by the SSPs, so what is the revenue accrued by the MNO? Okay. So the revenue, so let's try to understand this equation here. So now Fi is the amount of flow that is offloaded onto SSPI. So Fi times PM is the revenue collected from the user by the MNO. But of that revenue, Fi times Pi is the amount that is supposed to be paid to the SSP, right? So that means like this is the net profit of offloading Fi onto SSPI. Okay. Now, similarly, this is the net revenue made by offloading the monopoly flow Fj to SSPj, and the overlap flow is obviously going to be offloaded by the MNO to that SSP which serves sets the lowest price, right? So this is the revenue made by offloading the overlap flow, right? So very simple linear revenue model we are going to consider, right? And so already we'll see that it fetches some interesting results. Okay. Now, so what is the expected revenue? So we'll just take expectation with respect to the distribution of F1 and F2, right? So that randomness is in the amount of flow level seen at the SSP end. So similarly, I can talk about the revenue of generated by the SSPs also. So let's carefully go through these equations. So the details of the model will become much clearer here. Now, given the price vector, so what is the utility or the revenue accrued by SSPI, right? So suppose the price set by SSPI is greater than the price set by SSPJ, so it will not get the offloaded flow. It only has to serve the monopoly flow, and then Fi times Pi is the revenue it is going to make, right? So MNO has to pay this much amount, but then there is a cost model put here. So Fi times CS represents the cost or the revenue it has to pay for serving that much amount of flow. So this is actually the net revenue. Okay. Similarly, if Pi happens to be less than Pj, then SSPI gets to serve both the monopoly flow as well as the offloaded flow, right? And now in case when Pi is equal to Pj, we are assuming a model where half of the flow is offloaded onto SSPI and the remaining amount of offloaded flow onto SSPJ. Okay, so this is just for simplicity. So we can plug in any number alpha here. Okay, or we can also think of it as with probability 0.5. The flow is offloaded onto SSPI and with remaining probability onto SSPJ. Okay. So this is the revenue of SSP. And again, we can talk about the expected revenue. But since we are interested in a Bayesian setting, what is going to be more useful is going to be this conditional revenue. Okay. So I'm defining something known as this conditional revenue. So given that SSPI is observing low flow, so what is the expected utility made by SSPI? Okay. So this is the conditional revenue. Now, this is the conditional revenue given that the flow observed at the SSPI is FH, high. Okay, flow is high. So what is the conditional revenue? Okay. So in general, in the subsequent slides, I'll use this notation T. So T could be either low or high. Okay, and this is the conditional revenue given the type of type seen by the SSP. Okay, right. So now we have all the ingredients in place to set up the pricing problem as a Bayesian game. So I just summarize it here. So SSP1 and SSP2 constitute the player in the game. And what are the states of nature? So it could be low flow at both the SSPs. The flow could be low or high, similarly high, low, or it could be high at both the SSPs. And the probability distribution of on the states is simply given by this, right? So since the flows are IID, so it very easily follows. And what are the types of each of the SSP, right? So now the type could be low or high. So that means suppose SSP1 can only observe whether its type is low, right? So it has to maintain a probability distribution on what is going to be the flow of the other SSP, right? So these constitutes the types of this Bayesian game. And then what is the action space? As mentioned earlier, so it can set any price, but any price beyond PM or less than CS is not economical. So we'll fix this as the action space, right? So the SSPs can choose a price in this interval. And these conditional utilities or payoffs, I'll call it as the utility function. Okay, right. So once we have all these ingredients in place, so we can go ahead and define something known as the Bayesian Nash equilibrium. Okay. So now, so this exactly like the Nash equilibrium, but we only have this Bayesian setting because of these different types, right? So this is the standard Nash equilibrium definition. So if I deviate from so PIT star to any other strategy, so it is not going to be economical. Okay. So this is so this is the definition of the Bayesian Nash equilibrium, and our objective will be to characterize this Nash equilibrium. Okay. So let me go ahead and start characterizing the structure of the Bayesian Nash equilibrium. First, we'll look at the Bayesian Nash equilibrium in pure strategies, right? So this is the action space, right? So let's say that I fixed a flow level. Okay, so let's say that SSPI is observing a flow. It could be either low or high, right? So let's compute a threshold on this action space. Okay, so I'll proceed like this. Suppose SSP chooses to fix a price of, let's say, PM. It chooses a maximum price. So this much of revenue is at least guaranteed, right? So it may lose the overlap flow, but at least this much revenue is guaranteed. Okay. Suppose it chooses some price slightly less than PM, right? And so this is possible. It depends, of course, depends on the price set by the other player. But if it can accrue the overlap flow, so then this price is possible. Sorry, this revenue is possible, right? So I'll call this as VT. So it is a function of the action, right? And now you observe that if PIT is very close to PM, so this quantity is going to be greater than this quantity here, right? So that means that, and now as I start decreasing this PIT, this price, this quantity reduces, and so naturally there should be a threshold at which the revenue that I fetch, if I can accrue both the monopoly as well as the overlap flow, matches the revenue that I'll fetch if I only choose to serve the monopoly flow at the full price. Okay, so you'll get a threshold like this here, right? And now So the threshold can be easily computed here. So I just have to solve for p hat of t, and the threshold is of this form, right? And what this threshold suggests is, now if I choose a price less than this threshold, so it has to be, it is not going to be beneficial, right? So it's going to be dominated by some other strategy. Okay, so threshold serves like that exactly. Okay, so we have this lemma, so where we say that if the pricing strategy is less than this threshold, so then it is strictly dominated. Okay, so it's not very difficult. So so for instance, if you have a price less than p hat of t, so if I deviate to p hat of t, since I'm increasing the price, so it's possible that I can, so if suppose I get the overlap flow as well, so it's going to be greater than this, right? So if I choose this price, and it's not guaranteed that I'll get the overlap flow. If I get the overlap flow, I'll accrue a higher price. Okay, and now if I slightly increase the price to p hat of t, so the price is going to increase, or sorry, the revenue is going to increase. And then suddenly, if I switch from here to here, so I just serve the monopoly flow, and my revenue is same as what I would get here if I happen with this price, if I serve both monopoly as well as the overlap flow. Okay, and that way you can show that if any strategy less than p hat of t is dominated by this maximum price Tm. Okay, so this will enable us to shrink the action space much further. Okay, so that's what we have done. So these are just some simple properties of this threshold. So the threshold related to low flow is going to be less than the threshold related to high flow. This simply follows because this is increasing function of ft. Okay, and also we can ensure that this price falls in this interval. Okay, so that again follows from the form of this function. Right. So here is our key theorem in this context actually. So now, so we say that there is no BNEs in pure strategies for this pricing game. I'll quickly go take you through different cases that are possible. So before that, so there is a price range actually. So we had this original action space. So we kind of reduced the price range much further. So I'll call it as range 1 and 2. So range 1 is when the price set by the SSP is greater than the threshold. And range 2 is, we say that the price is in range 2 when the price exactly is equal to the threshold. Okay, so there are two possibilities. And now, so there are two price vectors comprising 4 different prices, right? So there are a total of 16 combinations possible once we have these two ranges, right? For each price, 16 ranges are possible. So, but we can capture everything into 3 different cases. So I'll very quickly take you through the cases. So here is case 1. Suppose for some SSP, both prices are in range 1. So what does that mean? So let's say for SSP J, the prices are not equal to the threshold. They are greater than the threshold. Okay. Now we can work out the details here. Suppose SSP high, the price of SSP high is in this range. So it can deviate to this interval and it can benefit actually, right? Because it is only getting the monopoly flow here. Here it can get the overlap flow, and the threshold itself is defined like this, right? So if you get the overlap flow, it's better off here. You are better off getting the overlap flow. Okay. Now, suppose the price matches the price set by SSPJ here, right? So what you can do, you can reduce your price marginally, right, by some epsilon amount. So you can always show there is an epsilon greater than 0. If you slightly reduce, you can acquire the overlap flow also, right? So you'll do better off. Here you are getting only 50% of the overlap flow. So here you'll do better off, right, by reducing the price marginally. Okay. So similarly, suppose your price is in this range, of course, you can always increase your price will increase, and the amount of flow you are serving is not going to get affected. Okay. So again, you are better off. So similarly, other two ranges, other two cases can also be similarly dealt with. Okay. So this is case 1. So again, case 2 is for both SSPs, one of the price is in range 1, while the other price is in range 2, right? That means for one of the SSP, so one of the price is equal to the threshold, okay, and the other price is more than the threshold. So similarly for SSPJ, okay. So in this context, actually, you can play around with these two other prices which are in range 1, and you can always show that there is a deviation possible. Okay. And so finally, there is one more case. So in let's say that all prices are in range 2, except for one of the prices. So now you can always show that you can deviate to this maximum price. One of the SSP can deviate, and it can be better off. Okay. So so this is essentially the proof technique here to show that there is no BNE in pure strategies. Okay. Yeah. So in view of this negative result, let's try to investigate what mixed strategies has to offer. Okay. So in this context, I will define mixed strategy as something like this, where each of these GIT is simply a probability distribution on the range on the interval. Okay. Now so suppose I know the mixed strategy of SSPJ, and let's say SSPI sets some price P, and the type of SSPI is T. It could be low or high. Okay. So what is the utility function? Okay. So let's write down the utility function. There are two possibilities. With probability theta, the flow at SSPJ is going to be low. With probability 1 minus theta, the flow is going to be high. Whenever the flow is low, so this is the probability that SSPJ, so since it's using the distribution, this distribution, so this is the probability that it's going to set a price less than P. So whenever it sets a price less than P, I just get the monopoly flow. Okay, so that this constitutes the revenue in that case. So this is the probability that the price set by the competing SSPJ is going to be greater than P. When it is greater than my price P, so I'm going to get both the overlap as well as the monopoly flow. Okay. So this is a very simple expression here, right? So I can simplify it. Okay. So I have an utility function of this form. And then I can talk about expected utility now, right? So if this is the mixed strategy that I'm going to use, then my expected utility is going to be of this form, right? I'll just integral over all possible P, right? And what is the mass I give on each of these P, okay? And also, if you see, the integration is simply over P hat, right? So anything less than P hat, I'll not put any mass, okay? Since those strategies are dominated, okay? This should be PM, so there's a notational error here. Okay? Right. So now again, we can go ahead and start defining mixed strategy Bayesian Nash equilibrium. So given a mixed strategy pair, so we define a Bayesian Nash equilibrium as something like this, right? So if I deviate from this distribution to any other distribution, right, I'm not better off, right? So my utility is only going to reduce, right? So this is simply the extension of the definition of Nash equilibrium to mixed strategy. Now, a mixed strategy, so we are particularly going to be interested in a symmetric Bayesian Nash equilibrium. So a mixed strategy Bayesian Nash equilibrium is said to be symmetric if both are equal to G star. Okay. So this work we kind of characterize only mixed symmetric mixed strategy Nash equilibrium. So determining non-symmetric Nash equilibrium, it's possible they exist. Okay. So something in the future we have to think about. Okay. Okay. Now, so this definition, right? So is not very constructive. So it's just so we can verify. But how do you construct a mixed strategy Nash equilibrium? Okay. So this proposition, so this is going to help us. Okay. So I'll just quickly take you through. So this is a very standard theorem. So you'll find it in any of the standard game theory books. Okay. So now I'll just specialize it to our case and also specialize this definition or this proposition to the case of symmetric mixed strategy. Okay. Now, suppose I have a mixed strategy candidate. Okay. I want to find whether it's a Bayesian Nash equilibrium or not. Okay. Now, all I have to do is look at the domain of each of these distribution, and now, let's say this is the utility I receive out of this distribution, and now we say that this pair constitutes a Bayesian Nash equilibrium if and only if on n. So if I fix any p in the domain of this distribution, so any p, so for any p that does not for which this condition holds, G star should not place any mass on that p. Okay, so that's the first condition. And now there should not be any other p where if I choose that price, I should not get a higher utility, right? Right. So so equivalently, this is what we are looking for, right? For any p in the domain of this distribution, this candidate distribution, the utility achieved should be same. Okay, and for p that are outside the domain, the utility should be lower. Okay, so I'll just illustrate that point through this diagram here, right? So here, so we have two distributions here. Okay, so these are candidates now. So we have to determine whether it's a Bayesian Nash equilibrium or not, right? So this is the distribution, and this is the, as I vary the price, this is the utility that I achieve corresponding to that distribution. Okay, and if you see in the domain of this distribution, the utility that I achieve remains constant, and outside the domain, it is lower than this constant here. Okay, so similarly for the other distribution also, right? If you see, if you observe in this interval, right, so it achieves the highest utility and it remains constant in that interval. So anything outside the domain of that distribution, so it is going to be lower than this constant utility here, right? So whatever we have here is a mixed strategy Bayesian Nash equilibrium. Okay, so we actually characterize that in this theorem. So this theorem essentially generalizes the result of Lee et al. Okay, so I'll mention about that result also. So this is the particular distribution that we obtain. Okay, so this is when this recall that we are talking about a symmetric case. Okay, so this is the distribution used by both SSPs. So when the flow is high, the price is fixed from this distribution. Okay, when the flow is low, the price is fixed from this distribution. Okay, and these thresholds, if you see, the intervals are disjoint. Okay, and how to compute the thresholds? So these are the thresholds. Okay, so the thresholds are given by these two equations here. Okay. Now, so how do we obtain this distribution? So so it follows from this expression of this utility function here. Okay, so essentially what do you need to do? So once you see this utility function, now you have to pick a distribution, right? So essentially you want a constant, right? On the domain of the distribution, you need to end up with a constant, right? That means, so there is a function of p. Somehow you have to pick a distribution that will cancel this function of p. Okay, so if you plug in this distribution, so that's going to cancel this function of p cleverly. Okay, and also you need to keep the domains disjoint, right? Otherwise, you have another distribution which is a function of p. So canceling that distribution is going to be cumbersome. Okay, so easiest way is to keep the domains disjoint, and once you keep the domains disjoint, you can just do a back calculation, back of the envelope calculation to come up with these distributions that will fetch you a constant. Okay, and now the next task remains to identify these thresholds, right? Now, how do you get these thresholds? So you can compute them iteratively. Okay, so the first threshold is simply obtained by solving at the highest price, right? So GS star So it's simply going to be 1, right? That's where your distribution ends. And for the second distribution, so it ends at QH, right? So now you already obtained QH by solving this. So you plug in here and you should be able to obtain the second distribution. Fine. Right. So now we can easily generalize that result to a setup comprising multiple flows. Suppose I have multiple flows like this. So now I can talk about mixed strategy for those multiple flows as well. Okay, so this is simply generalization of what we had earlier. Once you plug in n is equal to 2, it will boil down to that older case. Okay. Right. So now, what is the utility achieved by the SSP at this Bayesian Nash Equilibrium? Okay. So this is the utility achieved, and specifically when n is equal to 2, the case of low and high flow. So you can write down, simplify the utility to this form. Okay. Fine. So now, so this was the Bayesian framework, and the SSPs achieve some utility. Okay. So which is the average of the utility achieved when the flow is low and when the flow is high. Okay, U star. So we'll do some comparison with a non-Bayesian pricing scheme. So these essentially, so the base. Yes, go ahead.
Yeah. So, sir, the Bayesian settings you have considered. So,
yes,
I think you have considered the non-cooperative settings, and but they have complete information, right?
Non-cooperative, so incomplete information, because they do not know the type of the other player.
Okay, but you assume that they have the symmetric mixed strategy, right?
So we obtain a symmetric mixed strategy, yes.
Okay, but so non-cooperative as well as you have incomplete information.
Incomplete information, yes, yes.
Okay. Okay.
Right. Yeah. So so we will compare the Bayesian framework with a non-Bayesian framework. So the base paper remains this work by Lee et al. So I'll finally show the references also. So this is to a particular case where the SSPs are supposed to announce a single price, right? Alternatively, what the results of their work is limited to a scenario where the flow takes only one value. Okay, it's either low or high, but it's some FA, right? It's fixed. Okay. So it can be different also. It can be F1 and F2, F1 at SSP1 and F2 at SSP1, but there is no randomness in the level of flows. Okay. And also, it's not a private information. So the flow levels are completely known exactly at both the SSPs. Okay. So that's the model that was considered. And the original result comes from here. And what we have done is we have generalized this result to a setting comprising multiple flows. Okay. And so when we compare our so we call it as the flexible pricing scheme, because the SSPs are given the flexibility to dynamically set the prices. So this is flat pricing scheme because the SSP is supposed to announce a single price here. So there is no two different prices, right? So let's say that the a priori the SSP has to set a single price, right? So that we call it as a flat pricing scheme. And the difference in payoff is given by this. Okay, so this is the difference in payoff, and this is positive, so which means that the SSPs benefit in the flat pricing scheme in terms of revenue. Okay, so this for the particular mixed strategy. Okay, right. We also do a comparison in terms of price of anarchy here. So this is through numerical work. So we define this. This is the standard definition of price of anarchy. So UOPT is the optimal price, the optimal utility or the optimal revenue that the SSPs can make if they choose to cooperate among each other, right? If the SSPs choose to cooperate, then the best thing for the SSPs is to simply set the price to maximum and equally share the overlap flow among each other. Okay, this will fetch the maximum utility for the SSPs. Okay, and then So this is the actual utility made because the SSPs are non-cooperative. Okay. So I define this as the price of anarchy. And similarly, I can define the price of anarchy for the, so this for the flexible pricing scheme. I can similarly define for the flat pricing scheme as well. Okay. And so price of anarchy is always lower bounded by 1. And so we see that the flexible pricing scheme achieves a better price of anarchy, right? So lower POA means the utility achieved via the game theory solution is close to the social optimal. Okay. So this is we are just varying the. Sure. Yeah.
So the setup here, is it static or is it dynamic? So
yeah. So I should have mentioned this during the system model also. So what I'm assuming is like a time slotted system. So there is some traffic estimated traffic emanating from all the users, and the let's say that the estimate of the traffic remains constant for some amount of time. Okay. So during that interval, some prices are set, right? And once the users move away from the cell, okay, the flows are going to change. F0, F1, F2 are going to change, right? So again, a set of prices should be announced, right? So I'm assuming a completely dynamic, so a time slotted setup. Okay. So within the time slot, the traffic is going to stay constant for the time slot.
I see. But are you allowed to use the previous prices while deciding your new actions, or so can you use the entire information?
I understand. So that leads to a learning framework. Okay. But if the flows are IID across the slot, then such a learning will not be useful. But naturally, the flows are going to be there's some dependencies actually. So if you have a Markov chain kind of a structure, so it will lead to a learning framework, right? So right now we are just focusing on one slot and prices during that slot.
I see.
The slot could be bigger also. It could be of the order of 1 day. So in that context, in that case, so for instance, F0 overlap flow should represent an estimate of the average flow on that particular day. Okay, suppose some estimates of that nature is known, that will enable the SSPs to set the prices for that one particular day. Okay, or it may be of the order of few hours. So the price during these few hours is going to be this much. So very dynamically over slots, they can change the prices. So that's the assumption, but we are focusing on a single slot. So what you are mentioning may lead to a very interesting learning framework. We have not estimated, we are not worked in that direction yet.
I see. But even if you don't look at the learning aspect, do you think it's computationally simple to solve these dynamical games, the dynamic setup?
Dynamic setup, no. If we make the assumption that the flows across different slots are IID, then this is the solution already. If the flows are IID. Okay. So if it can gain some previous information, so I'm not sure actually how to. So perhaps we have to model that first, and then we'll be able to see if something from stochastic games can be invoked there. Right? So I cannot comment on whether computationally it's going to be much. The intensivity I cannot compute. I mean, I cannot comment on this now. Yeah.
Thanks. That's all.
Yeah, sure. Right. So so this is with respect to overlap flow. So we see that the flexible pricing performs better. So these are preliminary numerical results. So we plan to extend more in this direction. And this is when we increase the number of flow levels, right? So right now we are assuming only 2 flow levels. So the flow levels were of the the low flow was 5 and the high flow was something like 20. And now we are increasing more number between this 5 and 20, more number of flows, right? So that means we have a finite distribution of what the flow is going to be like, right? So once we have more number of flows, so we wanted to see what is going to be the price of anarchy. So we see that it eventually saturates to some value. Okay. So these are all numerical work. So we don't have any theoretical results as such yet. But we plan to see if there is a bound on the price of anarchy, right? And work in that direction also. Okay. Yeah, I think, yeah, I'm up with the time. So maybe I'll just quickly summarize. So maybe in a couple of minutes, I'll just spend on this MNOs offloading problem. See, we saw that the SSP benefit because of the flexible pricing scheme. But if we go and investigate what happens to the MNO, so the MNO is actually losing revenue when we switch from flat to flexible pricing scheme. Okay. And interestingly, the revenue it loses is exactly the revenue that is made by the SSP, right? So that way the total revenue is actually conserved when we move from flat to flexible pricing scheme. So one scheme favors the MNO and the other scheme favors the SSP, right? So now there's some kind of a trade-off now. So which scheme to use? There's competition between MNO and SSP themselves. So they can, so in this context, so we can formulate a Stackelberg game here. So these are very preliminary studies. So we are in the process of formulation itself. So now instead of what we are doing is we are introducing an offloading strategy. And instead of offloading the entire flow, a fraction of the flow, the SSP can choose to offload. Okay. And the remaining fraction, the MNO decides to serve by itself. Okay. So in that context, so there will be a new component added to the MNO's revenue. So this is the amount of flow that this is the revenue made by the MNO by serving the flow itself. Okay. So this is the cost of the MNO for serving 1 unit flow of traffic. So we can, so this is the standard definition of Stackelberg equilibrium here. So we want to jointly find an offloading strategy and a price vector. The offloading strategy should be such that if you deviate, it should not benefit. So this is actually an ongoing work. So, and also, yeah, so, and also this, the learning aspect, so we have thought about it, but of course the complexity we have to think about. So that's also one more interesting direction to focus. But currently our focus is on the offloading problem. So that will complete the setup. Both MNO also is taken into account, or MNO also is considered as a player. Right now, MNO is simply offloading. Okay, so it is not exercising its action to not offload. Okay, so we want to bring in that aspect also into the model. Okay, yeah. So yeah, just to conclude, so we are looking at this economics of data offloading. And essentially, we are using this framework of Bayesian games to formulate some interesting pricing problem. And our key results were to show that first, the negative result that there is no Bayesian Nash equilibrium in pure strategies. And then we went to mixed strategies, and we were able to characterize structure of a symmetric Bayesian Nash equilibrium. And we did a comparison between flexible and flat pricing schemes. And the takeaway there was that it's going to benefit the SSP, okay, but at the cost of the MNO's revenue. Okay, that means there is some kind of trade-off involved here, and we want to also study jointly this offloading problem using the framework of Stackelberg game. Okay, and yeah, so these are some references. So this is our paper with my student Sushma. And so this is the base paper where the non-Bayesian framework is studied. Okay, so this is in IEEE transition mobile computing. So the other interesting paper also. So for offloading, for mobile data offloading, so there's some option theoretic mechanism. So including our own paper with Professor Rajesh Sundaresan. So the option theoretic mechanisms are there, but there the utility functions require results strict concavity. Okay, so here we have a linear utility, and moreover, in our case, the utility functions are not continuous also. Okay, and also in this particular case, so we have this overlap flows as well. Okay, which is not there in the other work which use auction theory. Okay? Right. So there are other good references also I can share with you later if you are interested. And then, yeah, so with this, I would like to thank you.